All right, I am here to prove to myself in 5 years, when I forget all this stuff, that Navier Stokes is easy peasy. So to do that, I'm going to walk through a sample problem, like the easiest Navier Stokes problem you could do, and I'll probably do some other Navier Stokes problems as well. So what is the problem? So you've got two flat plates. The top one is moving at a velocity big U. The bottom one is moving at a velocity of 0. What is Navier Stokes going to do here? It's going to tell us what the velocity profile looks like. So it could look like a bunch of different things. It could look like this, where it's 0 on the walls, but then it reaches a maximum in the middle. It could look like this. It's not the best. There we go. Where it slowly increases, and then it's a maximum at the top. Or it could look like this, where it's linear, not parabolic. We can probably, just by looking at this, we can rule this one out, but we don't really know between the last two which one it's going to be. But the way we can figure that out is with Navier Stokes. Yeah, okay. So let's draw the axis. So I'm assuming that x is in that direction, y is in that direction, and I didn't draw that in a very good place. Let's draw it over here. X is that way, y is that way, and the height is h. Okay, now let's look at let's look at boundary conditions first, and then we'll do assumptions. Now, I used to just jump straight to the equation when I was an undergrad, but I learned kind of the hard way that it's very important to draw out the assumptions and the boundary conditions. It'll help a lot with these problems. So, boundary conditions. So at the bottom, right there, what do we know? We know that, I'm also going to say that the velocity has components in x, y, and z. The x component I'm going to call u. The y component I'm going to call v. Okay, so we know that u, that looks like a y. You know that u at y equals 0 equals 0. Why do we know that? So it's because of no slip condition. That's just like a condition that's assumed in mechanical engineering and fluid flow. It's a fluid right at a wall or right at a surface is moving at the exact speed of that surface. So on the bottom, it would be 0. But on the top, u at y equals h equals big U, because it's moving at the surface speed. Oh, there's so many freaking random lines. I hate that. Okay. Now, what else do we know? We know v, so that's a vertical component. That's the y component of velocity at y equals 0 equals 0. And why is that? Because if you have velocity going down, it can't go down because there's a freaking wall there. So it literally just can't go down. And it can't go up because it can't come from anything because there's a wall there. All it can do is go sideways, which it can't because of the no-slip condition. So it's literally not moving right at the wall. Let me erase those. Oh, one too much. Okay, likewise, at the top surface, we know v, y equals h equals 0. It's not equal to u because u is the velocity in the x direction. It's equal to 0 because, like I just said, it can't go through and it can't come out of the wall. Okay, those are the boundary conditions. And you'll see why those are important. Now let's talk through the assumptions. Where do I want to even do the math? I definitely want to do it below. So let's go through assumptions. Assumptions. So what are they? Let's assume it's steady state. That means that anything, the derivative of anything with respect to time equals 0. So it's not changing with time. Nothing's changing with time. Flow has been going through here for years, and it will go through here for years. So it's all steady. Next, we'll assume that it's fully developed in X. Let's assume that assumption basically means that this tube is infinitely long, and that right over here is the same as right over here. It's the same as right over here. The velocity profile doesn't change between those 3 points. And that's a very common assumption with this sort of stuff, so we're going to assume that. The way you write that is I'm going to move this right there. Write that is fully developed in X, and that means that the derivative of anything with respect to X is 0. Equals 0. What is W? W is the Z component of velocity. In this case, in this problem, it's 2D, and that is another assumption. 2D. That means W equals du dz v dz equals 0. Okay. I think we're good to start writing out equations. So, okay, yeah. Let's start with the math. The first thing you do, you always do this, is a continuity equation. I used to jump right to Navier Stokes. I don't anymore because you can actually get a lot of information from this. That's very important when doing Navier Stokes. So, continuity. What is it? It is du dx dy plus dw dz equals 0. Get rid of these random freaking dots. Okay, so we've assumed, kind of drew it too close to the other thing, but that's fine. We can assume that goes away because it's 2D, and one of our assumptions was W is 0, so W equals 0. This first term we can also get rid of because we assumed it's fully developed. So all we're left with is dv dy equals 0. So you're like, well, this is kind of lame. We can't do anything with this, but you are wrong. We can do a decent bit. So we integrate it, so we end up with v equals a constant. I'm gonna call it a. So now let's apply boundary condition. Let's apply this bottom one up here. That would be v at y equals 0 equals 0. And that would equal a, because v equals a. There's no y in this equation. It's just a all the time. So this means that a has to equal 0. And that means v equals 0. Now you're like, what the heck? Why do we do that? That's kind of a waste of time. Well, it is not a waste of time. You'll see why. Let's say you'll see why right now. So there are three components of the Navier-Stokes. There's x, y, and z. They're all very similar, but they're all for different directions. I'm not going to write out the z one, just because we assume 2D, all the terms are going to cancel out anyway. So let's write out the y one, because that'll be simpler. I'm drawing this stuff too close. So I do have it memorized because I've been writing it out a lot recently for my class. X. All right. It's a massive equation. This on its own, like, you can't solve this on its own. So we need to apply our assumptions, and you will see it will cancel out almost all the terms. So let's start over here. We can cancel out this first term because steady state, because we said that anything with derivative with respect to time is 0. Next, we can cancel out this term because we assumed fully developed. We can cancel out this term because v equals 0 because we found that up here from the continuity. If we didn't do the continuity, we wouldn't have found that, and that term would still be there, and then we would be like, what the heck do we even do? W is 0 because it's 2D. Now, is there any gravity in the x direction? In this case, no, because gravity points downwards. If we were looking at flow that looked like this, then there would be a component of gravity in that direction. But since our flow is, perfectly flat, we are chilling. Okay, so there's no gravity in this direction. dp dx, in this problem there's no. That's technically supposed to be stated. You would get that stated on like an exam or something. Okay. So that's 0. Now, what else are we left with? I just realized this is the Navier-Stokes in the x direction. My brain is just fried. This is not the Navier-Stokes in the y direction. That is okay, though. This fully developed derivative with respect to x, this 2D. So what are we left with? We are left with, on the left side, nothing. 0 equals d squared u dy squared. Okay, so what can we do? Well, we can integrate it, and we'll get du dy. I also swap the sides. Equals a constant. I'm going to call it a. So we can integrate it again, and we'll get u equals a y plus b. So this is a line equation. So right off the bat, you can tell that it's going to look like a line, and you could probably guess that it's going to look like that, and you'd be right. It won't look like the parabola kind of thing. Okay, so now let's apply the boundary conditions. So what are the boundary conditions for you? At the bottom, it's 0, and at the top, it's big U. BC's. U at y equals 0 equals 0. That equals a times 0 plus b. So that goes away. And you're left with b, that's not a b, equals 0. And then the next one is u at y equals h equals big U. That equals a y, but we replace y with h because y equals h. So this means that a equals u over h. Okay, so now final equation, u equals u over h y. That's it. So what does this mean? This means that at y equals 0, it will equal 0. And at y equals h, it'll equal h. So if we draw the profile, we got our tube there. Well, not a tube. I don't want to say that because that's cursed. It means we have to use radial coordinates. So at the bottom, it's 0. And at the top, let's say it's some velocity u. So it's going to be a straight line, because if you plug in 1/2 as y, you'll get u over 2. So that's right in between there. So it's going to be a straight line. Cool. That is Navier-Stokes in the X. Normally, that's the end of your problem. But in freaking grad school, they teach you that you also should write out the Navier-Stokes in the Y. And that will look like... minus. Not U. It's V. So, what can we cancel out? We can cancel out this term, steady state, this term, fully developed, this term, V equals 0, this term, and this term, 2D. Oh. This term, we can't cancel out, because in this problem, 100% of gravity is pointing in the y direction, because gravity is pointing down, and y direction is, we said it's pointing up. So we can't freaking cross it out. And in fact, well, okay, we'll get to that. So we can't cross that out. dp dy, let's also not cross that out, because that's what we're going to solve for. This is fully developed. Well, frankly, you can cancel out all three of these, and you can cancel out all of these, because v equals 0. So you're like, well, okay, cool. That doesn't leave us with much. And you're right. It would be 0 equals how much of gravity is in the y? All of it. So it would be gravity. And if it was tilted, we could do like a sine of theta or whatever, but it's not tilted. So 100% of the gravity is in the y. So it's just like that. Okay, I'm gonna rewrite this. So dp dy is on the left. That equals rho gravity. And actually I missed a negative. There's a negative right there. Because gravity is pointing down and we defined positive y as pointing up. Okay, now we can integrate it. You gotta add the constant. In calc, they teach you plus c, but no one really cares what it is. You can add whatever you want. Okay, now let's also assume that the pressure at y equals h equals 0. Let's assume it's gauge pressure, so it'll equal 0 at the top surface. I got lost. Easy. That would equal negative rho g y. It would be rho g h, because you plug in h plus a. So then we get a equals rho g h. So then we get pressure equals negative rho gy plus rho gh. And we could kind of group stuff together and we'd get rho g h minus y. Now what does this mean? If we plug in h, so at the top surface, we plug in h at the top, we should get 0. Is that what we get? Yep, because we get a h minus h, so that would be 0. But at the bottom, if we plug in 0, we'll get rho gh. So that means that the pressure is increasing as you go down. And that makes sense because submarines go underwater and they experience a lot of pressure the farther down they go. And that's why they are built in the shape of a pressure vessel. But yeah, so that's pretty much the easiest Navier Stokes problem that exists. Cool.